Okay, hi everyone, and welcome back to the HoTT-UF workshop in 2020. So now we'll have Andrew Swan tell us about going towards an enveloping infinity topos of the effective topos.
Thank you. So I wanted to start by saying briefly what the effective topos is and why I care about it. So it was a topos developed by Martin Hyland some time ago based on clean realizability. So it's been well studied by many people, and it has lots of interesting properties. So I guess the kind of motivating reason was that it satisfies all of the axioms of Russian or recursive constructive mathematics. So this includes Church's thesis, which states that all functions from the naturals to the naturals are computable. So it's kind of very non-standard axiom in some sense. But it also satisfies kind of more well-known standard axioms alongside it. So it's a topos. So it has dependent products, finite colimits, exact quotients, and a subobject classifier. And it has some choice principles. So it has enough projectives, and so because of this, it also satisfies countable choice. And it has a lot of interesting structure. So as an example of this, I wanted to mention the Lovir-Tierney topologies in the topos. So already in Martin Hyland's original paper, he showed that the Turing degrees embed in the Lovir-Tierney topologies of the topos. And there's also a kind of much more recently another class of Lovir-Tierney topologies by Sori Lee and Jaap van Oosten. So they use this more kind of combinatorial notion based on what they call SITE. So it's some kind of computable, well-founded tree. So that's the effective topos. What about, yeah, and also kind of another famous property is that it has this impredicative universe, but I won't talk about this so much today. Okay, so what about enveloping infinity toposes? So if we have an infinity category, then we can talk about the zero truncated objects of the infinity category. And so just as a notation, this is apparently usually written as tau zero. And this kind of definition in the classical theory of Grothendieck infinity toposes. So certainly it's in Lurie's textbook. I'm not sure if it was originally due to him or not. So an enveloping infinity topos is kind of the best approximation of a one topos by an infinity topos. So you start off with a one topos E, and this enveloping infinity topos, it has the property that if you look at the zero truncated objects of the infinity topos, and you get back the original topos that you started with. And there's also a universal property, that it's somehow universal with this property. Yeah, so it's a bit of a caveat. Lurie's definition is for Grothendieck infinity toposes. And I don't think I have a definitive answer to what an elementary infinity topos is at the moment. So I'm going to be a bit vague about this. So it could be something based on infinity categories. So quasi-categories, for example, which should be the kind of usual one that real infinity category theorists might like. But there have also been like other definitions. So you could also say a kind of model category is an elementary infinity topos. So apparently there was a definition along these lines due to André Joyal a while ago. Or if you like, I guess you could say that any model of homotopy type theory is kind of a elementary infinity topos, maybe. But I'll kind of stay a bit vague about this today. Okay, why do I care about enveloping infinity toposes? So in fact, this kind of first part, that the zero truncated objects are equivalent to the original topos, this already gives us a lot of nice properties. So if we have a enveloping infinity topos of the effective topos, then it would in particular satisfy Church's thesis, and it would satisfy countable choice, and it would satisfy propositional resizing. So in some of the proposed definitions of infinity topos, some people have thought about predicative notion where you don't have a subobject classifier or propositional resizing. But if you look at the enveloping infinity topos, then it does have to have propositional resizing, even if you don't assume it in the definition, basically because the effective topos is a topos, so it has a subobject classifier. So yeah, so it actually seems like quite difficult to come up with a model of homotopy type theory which also satisfies all of these conditions. So if there is an enveloping infinity topos of the effective topos, and if it is a model of type theory, then we should get all of these three things for free. And the final property is that there's this kind of observation by, or like a corollary of one of Weicker-Schulman-Spitter's theorems, that the Levier-Tierney topologies in a topos correspond precisely to topological modalities in the infinity topos. So I kind of mentioned on a previous slide that the Levier-Tierney topologies in the effective topos have like all this kind of rich structure, and then these appear in the infinity topos as topological modalities, so they're still there in some sense. And we don't need the universal property for this, so we can just kind of focus on constructing an infinity topos where the H sets are the zero truncated objects are the equivalent to the effective topos, and this would be kind of already enough to get something interesting, I think. Okay, so if you're thinking about how to build one of these things, one of the things that you might try first of all would be to just take one of these constructive models of homotopy type theory and then carry them out in the internal language of the topos E. And the first thing I wanted to talk about was kind of negative result, that this is not going to directly work, but it's a kind of, well, so we see afterwards that it's a good starting point, but first of all I say why it doesn't work directly. So the idea for the proof is first in Taichi Uemura's paper on cubical assemblies, where he showed that they don't satisfy propositional resizing. And then we use this again in our joint paper, where we showed that Church's thesis is false in the most kind of direct, straightforward, natural model of homotopy type theory in cubical assemblies. But today I want to kind of emphasize that this is really a kind of a general technique. So I kind of talk about slight generalization. So first of all, I just kind of say what I mean by the main currently known constructive approaches to models of HoTT and model structures. So I haven't looked in detail about at the Vandenberg Faber definition that Eric talked about earlier, but basically I mean everything except for that. So basically CCHM. Everything except for that and PCH basically. So we have this famous model, used Cohen, Kokan, Huber, and Wartburg. That's a constructive model of homotopy type theory in De Morgan cubical sets. And there's kind of like lots of other variants, including Cartesian cubical sets and Dedekind cubical sets. And various people have given model structures based where the fibrations are the same as the ones in the type theoretic definition. And yes, and then Taichi Imura used kind of kind of generalization of this result due to Orton and Pitts, and kind of a construction of the universe due to Licata, Orton, Pitts, and Spitters to get a model of homotopy type theory in cubical assemblies. And and today I also want to talk about the kind of constructive a constructed definition of a model structure on simplicial sets. So not the one that Eric talked about earlier, but another one by Simone Henry, Nicola Gambino, Christian Sattler, and Carol Sumila. So they constructed a model structure on simplicial sets. So I'll also talk about this. So so what all these things have in common is that various things, but one of the things they have in common is they have a kind of you get this string of 3 adjunctions. So you start off with a topos, or more generally a regular likely Cartesian closed category E, and then you can look at the internal presheaves in E, and then you get a string of adjunctions between these 2 categories. So you have like discrete objects, and then you have global sections. So this pi naught is connected components, and then you have this important Nabla here, which is the kind of right adjoint to global sections. So this kind of generalization of the result in the paper of Taichi is that if you have one of the variants of cubical sets, I think it have to be one of the variants with diagonals, so that's most of them except for PCH. Or simplicial sets. Okay, then you have this kind of maybe slightly funny statement that if you have a map F from X to Y in E, and if it's a cover or a surjection, when we look at the discrete, the map between discrete objects in the presheaves, then the original F that we started off with in E has a section. So, so I think to kind of demystify this, I just kind of quickly skip over the proof and look at one of the corollaries here. So, so this is a kind of a choice principle. So it's saying that certain surjections are split. So so if delta preserves covers and the axiom of choice holds for the original starting topos, the topos that we started with. So if F is a so so it's a straightforward proof. And then just kind of briefly, the idea for like proving this theorem is that is to use Nabla, the right adjoint to global sections. So it behaves, so Nabla of an object behaves kind of like the propositional truncation of delta of that object. So kind of in particular, we can like eliminate out of the real propositional truncation and use this to kind of construct a section. And then you just kind of mess about with adjoints and diagram chasing to get the section in E. And then so the other corollary is that we get this kind of recover the original result that Church's thesis does not hold in the pre-sheaves. Because Church's thesis says that this kind of a certain map here is Aqaba, and you can show that it doesn't have a section in any locally Cartesian closed category. So I guess this is related to the fact that Church's thesis is not compatible with the axiom of choice. And you notice that here this corollary does not mention delta, it's just about the pre-sheaves. Okay, right, so a more positive thing is that we can try and fix these models and make it so they do satisfy Church's thesis and other axioms. So again, in a joint work with Taichi and Miura, we showed that there's a left exact modality in the model of HoTT in cubical assemblies, whose reflective subuniverse provides a model of homotopy type theory where Church's thesis does hold. And then there's a kind of work in progress is to kind of generalize this. So first of all, this is now rephrased in terms of model structures. So this is using left Bruce field localization, which puts more structure on fibrations. So there's fewer fibrations, and equivalently, there's more trivial co-fibrations. You're adding more trivial co-fibrations. And then this is localization left exact. So the delta is a Quinion-Weiser joint. And then delta preserves all covers. And there's actually another property as well, which I didn't write down here, which is that it's non-trivial. So actually, by non-trivial, I mean that it doesn't just send everything to a weak equivalence, and that the natural numbers are fibrant. And in fact, every discrete object is, so I guess this follows from number 2. It's a Quinion-Weiser joint. So in particular, delta maps into fibrant objects. So this is a kind of non-trivial thing, non-triviality condition. And so this one is actually the only bit that uses the particular properties of assemblies. So in other words, this makes delta into a regular functor in some sense. And the effective topos is the reg X completion of assemblies. So this is exactly the same as having a exact functor from the effective topos to the zero truncated objects. And then you can show it has various nice properties. So it has to preserve certain things in the effective topos. In particular, it preserves all covers. And I guess the key idea to getting all covers instead of just some of them is a definition I call generic cover. So there's kind of various notions by Matthias Meny, like generic proof and generic mono, and so generic cover is something along those lines. And if you want to show that delta preserves all covers, you only have to show it preserves a generic cover. So that's kind of an idea which didn't appear in the previous paper. Okay, so overall, this is in cubical sets, but like recently I've been thinking about kind of an alternative way based on this HGSS model structure and some visual sets and some other ideas due to Jonas Frey, who's talking right after this talk. In cubical sets, the fibrations are already very structured, and we're kind of going with this by making them even more structured using the topological modality. Whereas on the other hand, in simplicial sets, the kind of key idea, as I understand it, is that you choose the definition of co-fibration so that the co-fibrant objects are well behaved. So specifically so that they have decidability of degeneracies. And then you kind of, if you want to use decidability of degeneracies for something, then you can just prove something for cofibrant objects and then use kind of diagrammatic proofs to extend it from cofibrant objects to all objects. And again, we can kind of go with this idea and try to get around the counterexample by making cofibrations even stronger, so that kind of cofibrant objects are even more special. And so in particular, there's a kind of notion of projectivity included in with them. So in this kind of, in the Henri Gambino Sattler-Semello definition, they define cofibrations as a really weak factorization system using the refactorization system of coproduct inclusions and split covers in sets. And then this is lifted to simplicial sets using Reedy definition. And if we're in a category of enough projectives, then we can replace this with different refactorization systems where you have all covers on the right, not just split covers. And then the left maps are coproduct inclusions where the complement is projective. So yeah, so just kind of summarized, I think that there's this kind of obstacle that I talked about, but there's also, for both cubical sets and simplicial sets, there appears to be ways to kind of fix them to hopefully try and get towards developing infinity toposes. So for cubical sets, they work very well for type theory. So if you want to use the extensional internal language of cubical sets, you can do that, kind of following Orton and Pitts. And also you end up with an actual model of type theory, including particular homotopy type theory. Topological modalities play a key role. And yeah, the main open problem is trying to ensure that data is essentially surjective. So I think that's actually not true for what I talked about today, but maybe there's a way to fix it. For simplicial sets, it's closer to classical arguments in homotopical algebra. You don't seem to have this problem with essential surjectivity, but as far as I know, the coherence theorem for interpreting type theory is still open for that model structure. So so this wouldn't necessarily give you a model of type theory. So yeah, that's all. Thank you for your attention.
Okay, thanks a lot. Let's give Andrew a silent round of applause. And does anybody have any questions?
Could you please go back to your slide on generic covers?
Yeah.
Right, so yeah, I was wondering, could you describe what a generic cover is in the category of assemblies, like in terms of the realizers? Is there a sort of nice description?
Yes, so I guess it would be, let's see. Yes, so I think lambda would be something like in non-empty subsets of the naturals, and then theta would be so for each non-empty subset, theta, the fiber in theta would be the elements. I think something along those lines.
Right. Okay. Thanks.
Any other questions?
So maybe I can ask something by means of clarification. So I think if you, at one point there was this theorem, maybe a few slides back from here, which talked about.
Which one?
Yeah, no, yeah, maybe, yeah, this one at the right. So there are no assumptions here about. So the conclude. It's a bit odd because the one of the assumptions seems to be something about a model structure, but then the statement itself doesn't mention anything homotopy theoretic.
Oh, yes. So cover should be the homotopical definition.
Ah,
Of
it's the
cover
homotopical. Okay, okay, okay.
Yeah.
Okay, that's what I missed. Okay. Ah, okay, I see.
Yeah,
Okay.
yeah. So yeah. In other words, surjection in the internal language of homotopy type theory, in
Oh, yeah.
the
Okay.
interpretation of homotopy type theory, if you like.
Right. I was reading. Yeah. Okay. Thanks. Yeah.
Any other questions? Okay, well, if not, let's thank Andrew again with more silent applause.
Thank you.
Thanks a lot.